Okay, chapter 24, practice problems. Let's go through some of these. So start with putting your name on it. All right, so it says plants convert CO2 and water into glucose in the presence of sunlight via, I think you guys know this one, you would have learned it in grade school, and that is photosynthesis. So photosynthesis is when plants take CO2 and water and convert it into glucose. All right, the next one, it says a monosaccharide with 5 carbon atoms and a ketone functional group. So if we have a ketone functional group, so we know this is a ketose, and if it has 5 carbons, it would be a ketopentose. So ketopentose would be the name for that one. All right, the next one we're looking for an aldohexose. So if we have aldo, we're looking for an aldehyde. We have one here, we have one here, we have one here. This one here, this is a ketose, so we can cross this one off. And this one here is also a ketose, so we can cross that off. So now we're looking for a hexose, and a hexose means it's going to have a total of 6 carbons. And so if we count here, 1, 2, 3, 4, 5, so we can cross this one off. Then here, 1, 2, 3, 4, 5, we can cross this guy off too. And then the last one, you can see it's got a total of 1, 2, 3, 4, 5, 6 carbons. And so the answer is D. Glucose is an aldohexose. I mean, if you had that memorized already, maybe you didn't even have to look at the answers. You just could have looked at the names of the sugars. All right, so the next one, it says, which of the following describes the relationship between D-glucose and D-fructose? If you haven't picked up on this, both of these compounds, D-glucose and D-fructose, have the same molecular formula, which is C6H12O6, but they have different connectivity, and so they would be constitutional isomers of each other, right? They have the same formula, but a bit connected in a different way. They're definitely not enantiomers. They're not epimers. They're not anomers. They're not diastereomers. They are just constitutional isomers. I mean, D-glucose is an aldose, okay, and D-fructose is a ketose. So obviously they are not simply diastereomers or something like that. Okay, next one is we're looking for a pair of enantiomers. So each one of these compounds has 4 stereocenters, and we're looking for the 2 compounds where every stereocenter is inverted. And if you look at compounds 2 and 4, you can see this stereocenter is inverted, this one is inverted, this one is inverted, and then finally this one is inverted. So those are definitely enantiomers of each other. So the answer is 2 and 4. So 2 and 4 would be B. So all we do is we look for inversion at each one of the stereo centers. All right, of the possible stereoisomers of fructose, including fructose, how many are going to be D-isomers? So remember, you're going to have the handout with the aldoses and ketoses on it. So if you draw the structure of fructose, so I'll just scribble it down here kind of quickly, but D-fructose looks like this. So we have CH2OH, then we have our carbonyl, and then we have something that looks like this. Okay, and then we have 1, 2, 3. There we go. So this is the structure of D-fructose. So this is D-fructose, okay? And it asks us, of all the possible stereoisomers for fructose, how many are D-isomers? Well, we know that when we have a family of sugars, that it's going to be a ratio of 1 to 1 for D and L, right? D are naturally occurring sugars, and L are synthetic sugars. Okay, and so we're mostly interested in the naturally occurring sugars. And so if we count the number of stereocenters, we have 1, 2, 3 stereocenters. So if we have 2 to the power of 3, that gives us 8 total stereoisomers. But we're going to divide that in 2 and say only 4 of them are going to be stereoisomers that are D stereoisomers. So it's 8 total, but 4 of them are going to be D and 4 of them are going to be L. So 4 of them will be D. There we go. All right, let's move on from there. It says, which of the following is the correct stereochemical configuration for D-mannose? So we have the structure of D-mannose here. And hopefully you remember that if your hydroxyl group on your chiral carbon is on the left-hand side, so we'll put here left-hand side equals S. And if your hydroxyl is on the right-hand side, so right-hand side, it's R or rectus, okay? So if we count this up, we've got SSRR, so we should have SSRR. Hey, what do you know? It's the first one, okay? So we have SS, I guess I should color code that. SS, and then we have R and R, just like that, okay? We don't have to go through each single one and expound on the content, whole pre-log rules for everything. Okay, next one is a really good question that students sometimes get confused on. It just asks you, which of the following structures represents beta-D-glucopyranose, okay? So when we're talking about a D sugar, okay, we always start with the same skeleton, okay? So we always start with our six-membered ring, okay? Not my best artwork, not my worst, okay? So there's our hydroxyl. So they're always going to be this, okay? We're always going to start with this. And it carbons 2, 3, and 4. So if we number our carbons, 1, 2, 3, 4, 5, 6, at carbons 2, 3, and 4 in glucose, the substituents will be equatorial, meaning the hydroxyl substituents, not the proton, okay? The hydroxyls will all be equatorial. So now, as far as carbon 1 is concerned, when it says beta-D-glucopyranose, the beta is talking about carbon 1. And so if it's beta, it's going to be pointing up, and so it would be up and equatorial. So this is beta-D-glucopyranose. Okay, so now we just have to look at the answers, and you can see that number 2 is the right one. Now, if we take this compound and we copy it and paste it, I just want you guys to be 100% sure on this, that if I just invert the anomeric carbon, if I just invert the anomeric center, so if I put the hydroxyl down like this, now it's gone from beta-D-glucopyranoside or pyranose to alpha, okay? So the Greek letter at the front refers to the anomeric carbon. All right, so this one is the correct one here. All right, let's move on from there. Next one, which of the following compounds are epimers of D-glucose? So first, we could draw the structure of D-glucose quickly. So let me just see if I can get it to align here a little bit. Okay, so if I go to CH2OH, and it says in the textbook that you should have the structure of D-glucose, how does he describe it? At your fingertips, okay? So you should have the structure of D-glucose at your fingertips. Let's see here. So there we go. All right, so this is D-glucose. Let me just finish it up here. So remember, an epimer means it's going to differ at one stereocenter. So we're just looking for one stereocenter that is different. And if you look at compound number 1, well, you can see that it's the same here, 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 but it's not the same here. So this one's different. I don't want to put it, I'll put it, I don't know, maybe I'll put a star by it, okay? Like that. And then if you look at compound number 3, okay, you can see it's the same here. It is not the same here. It's the same here and here. And so those two compounds just differ at one stereocenter. All right. And so those would be the two epimers. The other compounds differ at more than one stereocenter, so they're not epimers. So compounds 1 and 3 are epimers. So again, epimers, diastereomers that differ only at the stereochemistry at one chiral carbon. All right. Next one is this predict the major product for the following reaction. So we're taking this compound that has a hydroxyl group in it and an aldehyde in the same compound, and we're treating it with aqueous acid. Well, we have a nucleophile over here. This is a weak nucleophile, but we have a good electrophile here in the carbon of the carbonyl. And so in order to render that carbon of the carbonyl more electrophilic, what has to happen is, first of all, it's got to get protonated, right? So the first thing that's going to happen is a proton transfer, and then we're going to end up with an oxonium ion that looks like this. Now this is going to be even more electrophilic, and so now the hydroxyl group can come in as a nucleophile like this, and then if we count the number of atoms in the ring, we have 1, 2, 3, 4, 5, 6. So we have a 6-membered ring that's going to be formed. So let me just put some arrows here. So we're going to end up with something that looks like this. All right. Then we're going to have our so let's see here. So did I do that right? Yep, I did. So if we have our hydroxyl group like this, and then this is going to be protonated like that. So now if we number them, this is going to be 1, 2, 3, 4, 5, 6. So on carbon 4, I'm going to have a methyl group. here like this. And then the last step is just going to be a proton transfer. And so you can see that it's going to give me compound 1 after the proton transfer. So I'll just say here H2O is going to come in and it's going to pluck off this proton. And so, I mean, you could have just looked at this and said, well, I'm going to form a hemiacetal in this case. So I'm going to make a hemiacetal, and I'm going to end up with a total of how many atoms in my ring? 1, 2, 3, 4, 5, 6. And so the only one that could possibly fit the bill is 1 because it's a hemiacetal and we have 6 atoms total in the ring. And so the answer is going to be A. Okay, moving right along. It says, which is the correct Haworth projection for beta D allopyranose? So if it's allopyranose, we have to look up the structure of allose unless you have it memorized. But allose, I don't know if you remember this from last class, we said all of the, I mean, I'm being silly here. All of the hydroxyl groups are on the exact same side. So if we put in our hydroxyl groups, so they're all on the right-hand side, and therefore they're all pointing down. So if we tally up 1, 2, 3, 4, 5, 6. So carbons 2, 3, and 4, we're looking for substituents that are all pointing down. And we see that in number 1 and in number 3. All of the substituents are pointing down. But remember, the beta here, this beta refers to the anomeric carbon. Okay, the anomeric carbon, which is, I'll put here, AKA C1. So if I look at the number 1, you can see that this is an alpha D-allopyranose, but this one here, the hydroxyl group is pointing up on carbon 1, and so this is beta. So number 3 is going to have to be the right answer. And again, the hydroxyls on carbons 2, 3, and 4 are all going to be on the right-hand side. Therefore, they're all going to be pointing down in my Haworth projection. So the answer is going to be number 3 for this one. Which of the following compounds is a glycoside? Remember, if we have a glycoside, what we're looking for is an acetal. Okay, so if we look at the first one, we have a hemiacetal right here. Maybe I should use my yellow pen. We have a hemiacetal here. We have a hemiacetal here. But if we look at compounds, or if we look at compound 3, you can see we have an acetal here. And if you look at compound 4, we also have an acetal right here. So we have 2 acetals in compounds 3 and 4. And so that must be the answer. Okay, neither one of those is going to be a reducing sugar. Predict the compound or the product that's formed for each of the following reactions. So the first one, we're taking galactose. And galactose is just an epimer of glucose, but we'll pencil down the structure of galactose, which looks something like this. So we have 1, 2, 4. We have our hydroxyl group here, here. Just bear with me. I'll get this thing on here. So there we go. So this is D-galactose. And now if we take that and treat it with sodium borohydride, remember sodium borohydride is a reducing agent, and so it's going to make an alditol. So it's just going to reduce this. It's going to reduce this carbonyl down to an alcohol, and so the answer is going to be number 3. It gets reduced down to the alcohol like that. All right, number 14. Which of the following D-aldoses will produce an optically inactive product when treated with sodium borohydride in water? So what that's going to do, that would convert any of these ketones into an alcohol. So if I just kind of scribble over top of them, so DH2OH, just to put it in your mind's eye, okay? Okay, so if all these tops are identical to all of the bottoms down here, well, which one would end up being optically active? Well, we're looking for a compound that would be meso. And so the answer is going to be number 3, right? You can see that in number 3, when I reduce it, okay, so let's say I take this compound and I treat it with sodium borohydride in H2O. What I'm going to end up with, oops, wrong molecule. Okay, so let's redraw it here. We're going to end up with this CH2OH And then every hydroxyl group is going to be pointing to the right-hand side. And so I'm going to end up with a meso compound, which is optically inactive. It's got chiral centers. There's no arguing that. But at the end of the day, it's not a chiral compound. Why? Because you have a plane of symmetry down the molecule like that, okay? So this is meso, and therefore not optically active. It will not rotate plane polarized light. Okay, next one. Which of the following compounds is a non-reducing sugar? So let's take a look here. This one is going to be reducing because we have a hemiacetal here. This one will be reducing because we have a hemiacetal here. This one, there's no there is a hemiacetal. It goes carbon, oxygen, hydrogen. So we have a hemiacetal here. Whereas in this one, we go carbon, oxygen, carbon, oxygen, carbon. And so this one has an acetal, and therefore it cannot function as a reducing sugar. And therefore the answer is going to be number 3. Next one, we take xylose and we treat it with bromine and water. And remember, this is buffered to a pH that is equal to 6. And so when we do that, we end up oxidizing our aldose to an aldonic acid, excuse me. Anyhow, so first let's find the structure of D-xylose. So I've gone ahead and looked that up. And D-xylose is just an aldopentose, which looks like this. So 1, 2, 3 stereocenters. There we have this. Like that. And then we're going to treat it with our reaction conditions. So bromine and water at a pH that's equal to 6. And so we're going to oxidize to an aldonic acid. So I'll just take this compound and I will copy it and I'll put it over here. Okay, and we'll change the carbonyl from a aldehyde to a carboxylic acid. And there you have. So this is an aldonic acid. And this is D-xylose. Okay, now we're really cooking with gas. Only got well, there might be a few more. All right, next one. Predict the products for the following reaction. So for this one, we're taking D-galactose. And we actually drew D-galactose earlier, didn't we? Yeah, it's right here. So I'm just going to borrow it from this question. So this is our D-galactose. So I'll just copy that and bring it along. Work smarter, not harder, right? So we'll put the D-galactose right there. Okay. So when I take D-galactose and I treat it with nitric acid, I'm going to convert it from the aldohexose to an alderic acid. So that means I'm going to oxidize both of the terminal carbons. So I'm going to oxidize this carbon to a carboxylic acid and this one to a carboxylic acid. So right away we can cross this one and this one off because they aren't alderic acids. But if you look at 1, 2, and 4, you'll see that it's number 1 whose stereocenters, right, are all the same as the stereocenter for D-galactose. So this is the aldonic acid that's formed when you put D-galactose in nitric acid. Okay, next one. Which aldose would you expect or would produce D-ribose and D-arabinose when subjected to a Killiani-Fischer synthesis? So if we just draw one of these compounds, so if we take D-ribose, for example, so let me find the structure of D-ribose, and of course I'm looking at the handout. There we go. So Killiani-Fischer synthesis. Oh, okay. When you would make D-ribose and D-arabinose. Sorry, I was reading the question wrong. I'm like, I'm not getting something here. So if I just put the structure of D-ribose quickly, so it's an aldopentose. So we have all of our hydroxyls on the same side. Okay. So this is D-ribose. And so this is, we'll put here D-ribose. Okay. And then if I just copy that and paste it here, okay, and I'll change the color. All right, so this would be a D-arabinose. All I have to do is change, come on, change these two chiral carbons here. So I'm going to have my hydroxyl group and my proton here. There you go. So diarabinose. So diarabinose. There we go. Good. All right. So when we subject those to the Killian, or when we subject an aldose to the Killiani-Fischer, well, what is the aldose going to be? Well, it's going to have these two chiral centers in common. This one here. So if I draw that aldotetrose, it's going to look like this. So it's an aldose, and it's a tetrose, which has both the hydroxyls on the right-hand side. And so if I look at the aldotetrose, I see it's deerythrose. So deerythrose, erythrose, like that, okay? And when I treat that with the Killiani-Fischer conditions, step 1 is going to be HCN. Step 2 is going to be palladium, barium sulfate. I didn't mean to do that. Where am I? Barium sulfate and hydrogen. Okay, that's going to give me either one of those compounds. All right, let's keep going. Number 19, predict the products for each of the following, Killiani-Fischer synthesis. So if I take D-ribose, and you can see that I have D-ribose here, so I'll just borrow it. I'll say, oops, I didn't mean all that, but anyhow, we'll take it, and we'll put it right here. So there we go. So there's our D-ribose molecule. So we have D-ribose, and then it says predict the product for the following. So we're doing a Killiani-Fischer synthesis. So that means we're going to elongate the chain by 1 carbon. So we're going to end up with a pair of epimers. So I'm looking for the compounds that have all of the bottom hydroxyls on the right-hand side. So I'm going to end up with both compounds 1 and 5 in this case. So the answer is going to be 1 and 5. And again, you can see that these are epimers of each other. Epimers. All right, next one is a full degradation. So D-galactose is going to degrade to give us something. So if we draw the structure of D-galactose out, so let me see here. There we go. So let's draw the structure of D-galactose, which looks something like this. So this is D-galactose. 1, 2, 3, 4 chiral centers, like that. Galactose. Looks like that. Okay. Now, if I do a full degradation, what I'm going to do is I'm going to remove this chiral center. So I'm going to be left with these ones here. And so I want 2 hydroxyls on the right. So this one would be a compound. And let me see here. Yep, that's the only one that I'm going to get when I degrade that. So I'm going to end up with this compound here. So number 4 would be the correct answer. Which of the following is a reducing sugar? So remember, if it's a reducing sugar, we're looking for what? We're looking for a hemiacetal, okay? Not a glycoside. So we see the first one has a hemiacetal in it, so it's a reducing sugar. This one is a glycoside, so glycoside, so it doesn't have a reducing sugar. This one is sucrose, which you can probably recognize, and so it's not a reducing sugar. Either way, you can just try to find a hemiacetal and you'll find that there is none in here. So I'll just write sucrose on here. And then the last one, there's no hemiacetal in there either. So the only one that has a hemiacetal in it is A. So I'm going to scribble here. This is your hemiacetal speaking. No, this is a hemiacetal. All right, number 22. Which of the following disaccharides are alpha glycosides? So if we're looking for an alpha glycoside, we're looking for an alpha 1,4 linkage. So we talked about maltose, which had an alpha 1,4 linkage. Then we talked about cellobiose, which had a beta 1,4 linkage. Then we talked about lactose. And lactose, did I make a mistake here? So if you go into lactose, did I make a mistake in my answers? So let me check something quickly here. Just bear with me for 1 second. Okay, no, I didn't make a mistake. So, yeah, lactose is also beta 1,4, right? Beta 1,4. And then sucrose. So if you go back to the structure of sucrose, so sucrose had a linkage, and I told you, I thought I said that you didn't need to know it, but it actually is alpha 1, 2 is the linkage. So I'll write it down here. So we'll put sucrose. Sucrose is alpha 1, 2. Okay, now this question I know I got it from the publisher, so he thinks it's important, so I guess it's wise to know that. Okay, so sucrose and maltose. So I stressed these three, but make sure you know sucrose too. It's alpha 1, 2, and that is not a reducing sugar. Okay, let's see here. Number 23, it says, which of the following monosaccharides are produced when starch is completely hydrolyzed? Well, starch, you remember, was made of alpha, so it was alpha 1, 4 linkages of D-glucose. And so we're going to end up with alpha D-glucose when we hydrolyze it. The next one, I didn't give myself a lot of room to solve this, did I? But it asked for a Haworth projection and a chair of D-glucose. So let me solve 24 down here. So 24, if I write down the structure of D-glucose, so let's give it the old college try here. So D-glucose, gave myself way too much room here. All right, so D-glucose, 1, 2, 3, 4. And if I look at my handout, D-glucose looks like this and like that. There we go. Okay, so if I want to draw a Haworth projection, the way I do the Haworth is always the same. So I'm going to start out something that looks like this. And this part never changes. The same thing with a chair. If I draw a chair, this part, okay, with the oxygen here and CH2OH, this part never changes. These two are actually identical to each other, okay? They never change. Now, what it's asking for here is alpha D-glucose. So I know on my anomeric carbon, which is carbon number 1, that my hydroxyl is going to be pointing down here. And here it's going to be pointing down as well because I'm asked to draw alpha D-glucose. Now, for carbons 2, 3, and 4, so 2, 3, and 4, I see that the first two hydroxyls are pointing down, and the next one on carbon 4 is pointing up. So if I go carbon 2, down, carbon 3, down, that's even worse. Carbon 4, up, like this. So the same thing on the chair, carbon 2, down, carbon 3, down, and carbon 4, up, like that. So there you go. Now I've drawn the chair and the Haworth projection. So this is your chair, and this is your Haworth projection of both of alpha D-glucose. All right, there we go. Not too bad. Let's see here. Number 25 says, draw a chair conformation of the disaccharide formed when two molecules of D-allose are linked together by a 1,4 beta D-glycosidic linkage. So they're telling us that it's a beta linkage between the two sugars, okay? So if it's beta, that means that between sugar number 1, so if I just draw a quick sketch here, what that means, it's going to be going up like this, okay? And then it's going to be going to my other sugar, okay? So first, why don't we just draw a chair of D-allose, and then we'll worry about putting them together, okay? So why don't we just start with D-allose? I'm sure a lot of you have the structure of D-allose memorized. Let me just move this out of the way. Okay, we'll move this down here like that. Okay, so let's draw the structure of D-allose, and then we'll kind of build off of that. So D-allose looks like this. So it's an aldohexose, And all the hydroxyl groups are pointing to the right-hand side. So 1, 2, 3, 4. Every hydroxyl is on the right-hand side. Good. Okay. Now, if we draw a chair, we'll just take our time and draw a chair. It's going to look something like this. Okay, this part never changes. Now, we know it's a beta, so I'm just going to draw the beta anomer like this. And every other hydroxyl, so carbon 2, 3, and 4, they're all pointing down, okay? So this one's going to be down in equatorial. This one will be down in axial. And then this one will be down in equatorial like this. Now, I'll move this over a hair just because it's kind of ugly. So this is beta. This is beta D-allose. Okay, so now what we want to do is we want to put two of these together to make a 1,4-beta-D glycosidic linkage. So we want, let's write it down here so we can see it. We want a 1,4-beta-D glycosidic linkage. Okay, so here's what we're going to do. I'm going to copy the molecule, okay, and then I'm going to paste it here. Now, this is kind of a trick that I can do on the iPad, but in the interest of time, I'll just paste, I'll just paste the structure again, okay? And this is how they're going to be linked, is like this. It's going to be beta 1,4 because I can't change this stereocenter. If it's pointing down, it's got to be pointing down. But here, it's beta, right? It's pointing up. So I'm going to erase this hydrogen, this oxygen, and this hydrogen, and then I'll just bring this together like that, and there you go. So that is our beta. Here's my red pen. This is carbon 1, this is carbon 4, and this is beta here. So this is our 1,4 beta-D glycosidic linkage between two molecules of allose, of D-allose. And I think that's all the questions. All right.